Hi all, today we start discussing section 3.3. This is a small section. In this section we will discuss isomorphisms. If V and W are two vector spaces over the field F, so this F should be common to this V and W, then any one linear transformation T of V onto W is called an isomorphism of V onto W. That means T from V to W, both vector spaces should be defined over a common field F, and this T is 1 1 and T is on 2. Then we can say that this T is an isomorphism. So this is the definition of an isomorphism, and this section we will prove one theorem, theorem 10. Theorem 10 states that every n-dimensional vector space over the field F is isomorphic to the space Fn, that is F cross n copies of F. So we start with an n-dimensional vector space V. Dimension of V is equal to n, and we need to establish the existence of a 1 1 onto linear transformation T from V to Fn. That is our requirement. This Fn consists of n tuples x1, x2, etc., xn, such that xi belongs to F. This is the definition of Fn. So we start with an ordered basis V, consisting of the vectors alpha 1, alpha 2, etc., alpha n. Be an ordered basis of V. We start with this one. Now you can get, for any alpha belongs to V, then there is a unique expression. Then there is a unique expression alpha is equal to x1 alpha 1 plus etc. xn alpha n. So this alpha can be written as a linear combination of these alpha 1, alpha 2, alpha n uniquely. Okay. Now you define a map for linear. First you define a map T from V to this Fn, defined by T alpha is equal to this coefficient x1 etc. Xn, where alpha is this one, x1 alpha 1 plus etc. xn alpha n. Now we can easily prove that this T is a linear transformation, because when you take any two vectors alpha and beta belongs to V, you can get beta also have this expression w1 alpha y1 alpha 1 plus etc. yn alpha n for some yi belongs to F. Now you can consider C alpha plus beta, then that is T of C times alpha, that is C times this, plus beta. So when you add those quantities, you can get Cx1 plus y1 times alpha 1 plus etc. Cxn times Cxn plus yn times alpha n. Okay. Now the image will be the Cx1 plus y1 etc. Cxn plus yn, and this can be written as C times x1 comma etc. xn plus y1 etc. yn. Okay, so you can say that this is same as C times T alpha plus T beta. Okay, this shows that this T is a linear transformation from V to Fn. Now we will prove that this T is 1 1 and T is on 2. To prove T is 1 1, we need to prove that T is 1 1 first. To prove T is 1 1, we start with T alpha equal to 0. T alpha equal to 0 means T of x1 alpha 1 plus etc. xn alpha n equal to 0, where this alpha is equal to x1 alpha 1 plus etc. xn alpha n. This implies what is the image of this? That is x1 comma x2 comma etc. xn equal to 0 when this n tuple is 0 in Fn, such that Fn means this xi equal to 0, I equal to 1, 2, 3 etc. n. Consequently, what is alpha? Alpha is 0 times alpha 1 plus etc. 0 times alpha n equal to 0, that implies alpha equal to 0, that is t is 1 1. T is 1 1, and the dimension of, along with the condition, the dimension of V and the dimension of Fn both is equal to n. Okay, now we are given that dimension of V is also n and dimension of Fn is also n. Then we can get 1 oneness implies invertibility. Okay, so this implies T is invertible using the previous theorem, theorem 9. Okay, using theorem 9 we can get T is invertible. That means T is 1 1, T is onto, and T is a linear transformation. Then this T establishes an isomorphism from V onto Fn. So this shows that V is isomorphic to this Fn. Okay. In order to prove two vector spaces are isomorphic, we need to establish the existence of an isomorphism from V onto the other vector space. So this shows that V is any n-dimensional vector space is isomorphic to Fn. With this, we can conclude section 3.3 as well. In the next lecture, we will discuss the representation of a linear transformation using matrices. Thank you.